2.1, rectangular coordinates and graphs. Well, now we're going to start into dealing with graphing it, the rectangular coordinate system. To start into that, we're going to talk about ordered pairs. Now, I would be surprised if any of you are not familiar with ordered pairs. Ordered pairs are just where you have two pieces of data that relate to one another, and you put them together in an order, thus creating an ordered pair. Maybe you have height and weight. They're related to one another. In fact, they make more sense when you relate the height and weight of a single individual as opposed to the height of one person and the weight of somebody else. When dealing with the coordinate system and plotting them, we generally create ordered pairs that we call x and y, where x is the independent variable and y is the dependent variable. Meaning that x is where it starts and y is related to x and changes according to x. Or you can take x as the input and y as the output. Plug in a certain x value, you get a certain y value out. Now these ordered pairs, when we're dealing with the rectangular coordinate system and graphing, those represent points. And many times when we label a point, we use a capital letter. So maybe we call this the point P, with A and B as the x and y values associated. But x and y, what do we mean when we're dealing with this x and y? Well, let's look at the rectangular coordinate system. The rectangular coordinate system basically deals with two number lines. One which is horizontal and one which is vertical. The horizontal one is called the x-axis. The vertical one is called the y-axis. In the middle, this point right there is called the origin. And that point is also represented by the ordered pair 0, 0. So you can think of this x-axis as a number line with the centered at 0 and going positive that direction, negative this direction. And the y-axis is another number line where it's going positive up. I'm just going to put those on there just so we can make sure we remember this. So y is positive going up and negative going down. X is positive going right and negative going left. We have that also. You notice that these two axes break this coordinate system into four parts, which we call quadrants. We start with this quadrant, we call that quadrant number 1, and we use Roman numerals for this. Don't write 1, 2, 3, 4 in your normal numbering. Use Roman numerals and we go counterclockwise, so 1, 2, 3, 4. And I will point out something with this, that in the first quadrant, all of our ordered pairs will be positive, positive. You'll have a positive x value and a positive y value. In the second quadrant, be negative, positive. Negative x value, but a positive y value. In the third quadrant, they are both negative. A negative x and a negative y. And in the fourth quadrant, positive, negative. The x value is positive, we're back on the right side of the plane, but our y value is negative, we're in the bottom portion of this. Also, I want to point out, when you're dealing with plotting points on this rectangular coordinate system, just think of order of events. you started learning numbers in the number line with a horizontal line. Therefore, that is the first one. You start with horizontal, it starts there, and then you added a y-axis, this vertical line. So you can always remember the x-axis gets taken care of first, and then the y-axis, or the horizontal axis, gets taken care of first, and then the vertical. Also remember that our ordered pairs are done in XY, alphabetical order. So the value is XY, alphabetical order. The axes, the x-axis is the horizontal, that's what comes first. The y-axis is what came later, that's what comes second. So when we're plotting points on our coordinate system like this, it should be relatively easy for us to remember that you plot the x value going along the x-axis first, and then the y value going along the y-axis. So that's the way we're going to do it. So I'm going to get these things out of the way here so we can actually plot some points. Sometimes you question whether it's quicker to erase that or quicker to erase the whole thing and get rid of it. I'm going to get rid of these negatives and positives too, because I want to practice without them, get rid of that. So yeah, I probably could have just erased it quicker. Okay, well I want to have some marks on here. And I'm going to number these 2, 4, 6, 2, 4, -2, -4, -2, -4, -6. Whenever you're numbering your axes, just like when numbering a number line, you should have consistent indices. In this case, I counted by 2, 2, 4, 6. If you want to count by 5s, fine, 5, 10, 15. If you want to count by 1s, if you want to count by 3s. If you want to count by 3/7, go ahead, but be consistent with it. 3/7, 6/7, 9/7, 12/7, right? So be consistent. Don't number 2 and then 5 and then 6 and then 7 and then 12. Be consistent in your numbering of your axes, and you should always number them. When you are asked to plot something, be it points, a graph of a curve, a shape, always number your axes. Don't leave it to the person reading your plot to guess what the numbering system is. Especially not if that person is a teacher, because they'll automatically take off a point for the fact that you did not number your axes. So now I have that, I'm going to list 3 points. We'll call them P, Q, and R. So P, Q, and R. P is -2, 5. Q is 4, -1. And R is -3, -4. So I have these 3 points, and I want to plot these 3 points on this coordinate axis, and I want to label them, meaning that once I find where point P is, this -2, 5, I want to label that as P. I don't want to put down that it's -2, 5, I just want to label it as P. So here we go. So -2, 5, remember you start with the x-axis, and that's the first variable, so -2, we come over to -2. Just keep your eye on that. Don't mark that. That's not the point, that's just how far to the left we're going to go. And then y is 5, so we're going to go to +5. So notice we went to -2, we go up to +5, and where they meet, that is our point. So you can think of it as someone told us to go 3 blocks to the west, and then 5 blocks north. That's where we end up. That's where it put us, and that's point P. Q is 4, -1, so we're going to go 4, minus 1 takes us to there. There's Q. And then R, negative 3, negative 4, negative 3, negative 4. And we have R. So that's us plotting 3 points. Now I am going to tell you that just because I had you plot 3 points does not make this a triangle. So don't just automatically connect dots whenever you plot points. One of the biggest pet peeves I have with graphing is the fact that people will see, oh, I had to graph 3 points, and they'll draw a triangle out of it. It's like, no, they're just 3 points. That's all they are. Okay, so we plotted that. Now, what I want to go into here is, since we can plot them, I want to look at distance between points. So let's look at that. First, I'm going to get rid of this coordinate system because I'm going to look at the distance between points on a number line. So if I have a number line, the distance between points A and B, A has some value, I'm going to call it x sub 1. B has some value, x sub 2. The distance between them is just the difference in those values. Now realize that distance is always positive. You can't have a negative distance. Sometimes we use sign to indicate direction. Plus 5 means I went 5 miles east. Minus 5 means I went 5 miles west, but the distance is still 5 miles. So when we are finding the distance between these, I'm going to say D, AB, so the distance between points A and B is equal to the absolute value of x sub 1 minus x sub 2, which is equal to the absolute value of x sub 2 minus x sub 1. So it doesn't matter which one you start with, since we're going to take the absolute value of the difference anyway, it doesn't matter which point we start with. So let's say we switch to red here just to mix it up a little bit. Let's say this is 5, and that's negative 2. And we want to find the distance between these. Then the distance between 5 and negative 2, actually, since I had said A and B, let's just change the order of that. Negative 2 and 5 is equal to, it doesn't matter, I can take whichever one. So I'm going to say the absolute value of negative 2 minus 5. Negative 2 minus 5 is negative 7. Absolute value of negative 7, which is equal to 7. So the distance between it is just the difference between the two values without the sign. And that's how simple it is to find the distance on the number line. Well, things change a little bit when we go to the rectangular coordinate system. Because now not only can things move left to right, but they can also move up and down. But that's not as scary as it may sound initially. And the reason it's not as scary is because we already have the tools to work with that. So if I have my rectangular coordinate system here, and I'm just going to give a quick demonstration without doing anything fancy with it. I just want to show what I'm looking at. You remember this is x and that's y. Now if I give 2 points on this coordinate system, so I'm just going to choose this point here and this point here. It really doesn't matter what 2 points I choose for this particular demonstration. The distance between those 2 points, D, let's call this P and this Q. So the distance from P to Q, notice that that can be found by looking at a right triangle. Where the vertical line is the change in y values from the 2 points, and the horizontal line is the difference in change of the x values of the 2 points. So that's delta y, that's delta x, remember delta means change, and then we've got this distance here. Well, if I know this side and this side, or the two sides of a right triangle, can't I find the hypotenuse just by using Pythagorean theorem? So therefore, the distance formula for 2 points in the rectangular coordinate system is simply the square root of x2 minus x1 squared plus y2 minus y1 squared. It's just Pythagorean theorem. So find my difference between my x values, find the difference between my y values, and we've got it. So looking here, if I have these numbered as 2, 4, 6, 2, 4, negative 2, negative 4, negative 2, negative 4, negative 6, if I have it numbered like that, then we can see that the point P is negative 2, 1, and that the point Q is 2, negative 3. Then using our distance formula here, I can find D by saying is equal to the square root of x2, well I'm going to call it 2, so x2 is 2 minus x1, negative 2, squared, plus y2, negative 3, minus y1, 1, squared. 2 minus negative 2 is 2 plus 2 or 4. The square root of 4 squared plus negative 3 minus 1 is negative 4. Negative 4 squared is, okay, so we'll just say negative 4 squared. Square root of 4 squared is 16. Negative 4 squared is 16. Notice we don't have to deal with absolute values here because when we square it, it's going to get rid of the negative anyway. So 16 is equal to the square root of 32. 32 is 16 times 2, so is equal to 4 square root of 2. So the distance between point P and point Q is 4 radical 2. So that wasn't too bad. Well, let's grab another random point and see what it, or I should say random 2 points and see what the distance is. I don't need to draw it out this time because we know the idea behind it. We're going to create a right triangle using the x values and the y values and find the hypotenuse. So let's say we have the point -3, 1 and another point 5, 4. And we want to find the distance between these points. The distance is found simply by taking the square root of 5 minus -3 squared plus 4 minus 1 squared. 5 minus -3 is 5 plus 3, or 8 squared. 4 minus 1 is 3, so 3 squared. 8 squared is 64. 3 squared is 9. So the distance is equal to the square root of 73. 64 plus 9, 73. And I don't see that I can simplify that anymore. So there's our distance, the square root of 73. Now realize when we're looking for the distances, unless we're dealing with a word problem where we really need to get it to a certain unit or whatever, leave it in the cleanest form that you can, but don't plug it into a calculator to approximate this. This is an exact value, the square root of 73. You plug this into your calculator, you're going to get an irrational number. And it's more accurate to do this. But if you're dealing with a word problem where this is going to give you the distance in feet from one person's house to somebody else's house, then of course you've got to take it to the point of having an actual value. Nobody wants to be told, oh, it's the square root of 73 feet. What exactly does that mean? Well, in that instance, it doesn't mean much of anything. Now, a use of this distance formula is the converse of what gave us the distance formula. Given 3 points that form a right triangle, you can find the distance between any two of those points. Also, given 3 points, if we can use the Pythagorean theorem, or I should say, if the distances between those 3 points conform to the Pythagorean theorem, then we have a right triangle. If the sum of the distance between 2 points and another 2 points is the same as the distance between the other 2 points. So if you have points A, B, and C, and the distance between AB plus the distance between BC is equal to the distance between AC. So if the distance between these 2 points and the distance between these 2 points add up to that distance, then they must all be on the same line. So if the distance between AB squared plus the distance between BC squared is equal to the distance between AC squared, we have a right triangle. If the sum of those distances is equal to the other distance, then we have what's called collinear. Collinear, meaning that they're all points on the same line. Well, let's take a look at some examples and see if we can determine whether we have collinearity, meaning they're all in the same line, whether we have 3 points that form a right triangle, or we just have 3 points. So we'd say neither. It's neither a right triangle, nor is it collinear. So let me grab those 3 points. R is the point 0, -2. S is the point 5, 1. And T is the point -4, 3. Now when we do this, it just does take a little bit of effort because we really have to find 3 distances, right? So we're going to have to use the distance formula 3 times. So for R and S, so the distance between R and S is equal to the square root of 1 minus -2 squared plus 5 minus 0 squared. 1 minus -2 is 1 plus 2 or 3. 3 squared is 9. 5 minus 0 is obviously 5. Squared is 25. 9 plus 25 is 34, so the square root of 34. The distance between R and T is equal to the square root of, and I just realized I wrote that backwards, but you can trust me on this. I went to my y values first, and then I did my x values. So I did y squared plus x squared. I just want to clarify that that's what I did. It works for Pythagorean theorem, and unfortunately it's a habit you get into when you're dealing with slopes. They tend to work, you remember to do the y values first and then the x values. What matters here is the fact that I kept my y values together and found the distance of my y, and I kept my x values together and found the distance of my x. I'm going to do the next one correctly, doing x first and then y, but like I said, commutative property of addition, it doesn't matter which one you do first. So RT, we're going to do -4 minus 0 squared plus 3 minus -2 squared. -4 minus 0 is -4. -4 squared is 16. 3 minus -2 is 3 plus 2, or 5. 5 squared is 25. The square root of 16 plus 25, 41. So the square root of 41. Now let's get the last one, the distance S to T. The square root of -4 minus 5 squared plus 3 minus 1 squared. -4 minus 5 is 9. -9 I should say. Squared is 81. 3 minus 1 is 2. 2 squared is 4. The square root of 85. So now we look at these and go, well, what does this do for me? Well, first thing I want to look at is if I square this, and notice that we have 2 smaller ones and a larger one. When you're dealing with right triangles, obviously the longest side would be the hypotenuse, and the other 2 would be the other 2 sides. If you're dealing with collinearity, then the longest side, the longest one, would have to be where the other 2 add up to, so you take the 2 smaller ones and add them up to get the longer one. So looking for a right triangle, we can do this pretty simply because it's the square of this plus the square of this is equal to that. Well, the square root of 34 is 34. The square root of 41 is 41. The square root of 85 is 85. So 34 plus 41 is 75. That is not 85. So therefore, not a right triangle. So that is not the case. Now we have the square root of 34, square root of 41, and square root of 85. We want to see if those are the same. That one's not as quick and easy. We can't just take, okay, square them all and see what happens. We actually have to look at those values. So plugging it into your calculator, see if they come out about the same, can work. So I'm just grabbing my calculator. Technically my roommate's, my office mate's calculator. We're in the square root of 34. Which gives us about 5.83. The square root of 41. About 6.40. So we're looking for 12.23. Which, without even going any further, we should be able to recognize the square root of 85 is going to be just over 9. So, no, not collinear. So therefore we say neither. We went through and we verified it's not a right triangle because the sum of the squares of those two sides is not equal to the square of that side. And it's not collinear because the sum of those two sides is not equal to the length of that side. So that's looking at collinearity, right triangle. And yes, you will run into cases where it turns out to be a right triangle. Yes, you will have times where it turns out to be collinear. If it was a right triangle, then, and I like this with right triangles really easy because once you've got it in the form square root of this, square root of this, square root of this, all you have to do is look at what's under the radicals, add up the two smaller ones and see if they come out to be equal to the larger one. Whereas for collinear, you have to approximate them and see if it comes out. And realize that you want it to be really, really close if you're dealing with collinear, because it's very possible you could have 3 points that are almost collinear, therefore the distances come out close but not the same. So you want to be very precise when you're dealing with that. I didn't have to be so precise because this obviously was not collinear, it was way too far off. But it's also obviously not a right triangle. I will also warn you, do not plot the points on a rectangular coordinate system and make your decision from that. And the reason I tell you that is because just because something looks like it's a right triangle, or just because something looks like it creates a line, does not necessarily mean that it really does. So don't eyeball it. Don't just look and plot the points and say, well, that's a right triangle, or well, that's collinear, because there's no guarantee from that. Another thing that I want to cover is the midpoint formula. Given 2 points, the midpoint is the middle point between them. And it is found simply by averaging the x values and averaging the y values. Because if you think of 2 points drawn on a rectangular coordinate system, the midpoint's going to be, if I just put these, just giving myself some horizontal and vertical things here, the midpoint's going to be halfway between them vertically. So about right there, and it's going to be halfway between them horizontally, about right there. And that's your midpoint. That's where your distance is going to be. So when we're finding the midpoint of 2 points, all we're going to do is average the x values, average the y values, and create our new point. The formula that we're going to use, therefore, for the midpoint is just going to be x2 minus plus x1 over 2. And I could actually do that as x1, x2. Again, one of those things you get used to putting the 2 first and then the 1 second for the subscripts when you're dealing with either slope or you're dealing with the distance formula. You get used to doing that. You don't have to for this because you're adding them. So x1 plus x2 divided by 2 and y1 plus y2 divided by 2 will give you your midpoint. So if we have the points 3, -7 and 2, 4, and we want to find the midpoint, then all we're going to do is we're going to add up the x values, 3 plus 2, and divide that by 2, and the y values, -7 plus 4, and divide by 2. We're just averaging. 3 plus 2 is 5, so 5 halves. 7 plus 4 is 11, -7 plus 4, careful about that. -7 plus 4 is -3. So -3 over 2, or -3 halves. So that will give us our midpoint between those 2 points. Nowhere near as painless as nowhere near as painful as you thought it was going to be. Much less painless. Much less painful. Boy, I'm just determined to make this painful for you. Much more painless? You don't really say that, do you? Definitely not as painful as you thought it was going to be. So just average the x values, average the y values, and that will give you the point. And if you think about that, that's exactly what you do on just a standard number line. If you want to find the middle point between 2 points on a number line, you just average the 2 numbers. That's the middle. It's a measure of center. Okay, so the last thing I want to go into is dealing with graphing equations with 2 variables. X and y, those inputs. And how do we do that? And there's a few ways that we can do that. In fact, there's numerous ways you can do that depending on what we're working on. What we're going to talk about right now is graphing it by plotting points. So if I have the equation y is equal to 3x minus 2, and I want to graph that equation, which actually we should be able to see that that is a line that's a linear equation because it has a degree of 1. There's no variable that has a higher degree than 1. So therefore that's going to be a linear equation. It's going to create a line, which makes our life easy because if we're going to plot it and get it shaped, we know it's a line, so you really only need 2 points on a line to plot it. It's always a good idea to grab a 3rd point just to make sure that they're collinear and that you actually get a line. A 3rd point helps to cover for if you make any mistakes. You go, oh, wait a second, that didn't work out. They didn't come out on the same line. So, if we're going to do that, we need to plug in a value for x or a value for y and then just solve for the other one. Now, it should be relatively obvious that if we have y by itself, plug in some values for x, and the simplest values to use in mathematics are 0 and 1. So I'm going to plug in 0 for x, and I'm going to plug in 1 for x, and then I'll plug in -1, so I'll give myself 3 points. Now I can do this creating a little table, x, y, and I can go -1, 0, and 1. And then see what my results are. If I plug in 0 for x, start with the easiest one, right? 3 times 0 is 0, minus 2. So we end up with -2. If I plug in 1 for x, 3 times 1 is 3, minus 2 is 1. And if I plug in, oops, put it in the wrong spot, 1. Never do videos late at night. And if I plug in -1, 3 times -1 is -3, -3 minus 2 is -5. And we just found 3 points, and we could plot those on a coordinate system, and we would see that it creates a line. I'm not going to take the time to do that on here. First of all, I have to draw graphs, grids, lines, and everything on the whiteboard, and that's not so pretty always. Secondly, we've already covered how to plot these points, so you should be able to take a look at that and plot them yourselves. Also, you can verify that they're collinear by finding the distance between each of these and verify that the distance between this point and the distance between this and this point add up to the distance between the first point and the last point. So that's how we can plot it. We just need to start plugging in some points. Sometimes, well, first of all, we don't always have linear equations. Secondly, we don't always have y equal to something. Maybe our input is what's by itself, and the output is not. So let's take a look at an example of that. X is equal to the cubed root of y plus 1. Well, if I'm going to plot this, I can just plug in values for y and see what x turns out to be. So that's an option. X, y, and remember, 0, 1, -1, those are easy, so -1, 0, and 1 for y, and now I plug that in and I get x. So -1, -1 plus 1 gives me 0. The cubed root of 0 is 0. 0, 0 plus 1 is 1. The cubed root of 1 is 1. 1, 1 plus 1 is 2. The cubed root of 2, ooh. We're going to have to approximate that one. Right, the cubed root of 2, it's going to be something a little bit larger than 1. But we can plot points that way. Now, the one thing we notice here too, right there is, boy, that's ugly. That did not give us something nice to work with. So what's another option? Another option is we could solve this for y. And that may make our life a little bit easier. So if I want to solve this for y, well, I've got the cubed root, so how do I get rid of a cubed root? I cube both sides, so I say x cubed is equal to y plus 1. Remember, since it's cubed, you don't have to deal with a plus and a minus in there. And then to get y by itself, I'm going to subtract 1 from both sides, so I'm going to say y is equal to x cubed minus 1. So now I have an equation that I can work with, and I'll create an additional little table for x and y, and I'm going to use -1, 0, and 1. If I plug in -1, -1 cubed is -1. -1 minus 1 is -2. 0 cubed is 0, minus 1 is -1. 1 cubed is 1, minus 1 is 0. And I want to point out with this is obviously not going to be a line, it's a nonlinear equation. So we would have to plot numerous points unless we have some other information to help us understand how to graph this. I will also point out that notice when we started with y equal to -1, we got 0 for x. When we started with 0 for x, we got y equal to -1. When we started with 0 for y, we got 1 for x. When we started with 1 for x, we got 0 for y. So it worked quite nicely, and it did function either way. Doing this put it to where it was easier for us to find values. I didn't have to use a calculator to find anything here. I would have had to use a calculator to get a good estimate of what the cube root of 2 is. So all of these things can work to our advantage. Sometimes manipulating the equation can make our life a little bit easier. So, rectangular coordinates and their graphs.